Good morning. For the second session today, am I speaking loud enough? Like everybody can hear me? Great. First I want to thank the organizers for having me here and learning about this interesting network that has been put together. Very interesting. And I will talk about cold atoms in optical cavities. And I will cover, two themes, if you want. One is the possibility of doing quantum many-body physics with such cavities where you place cold atoms inside. And a second theme will be super-radiant lasing using a narrowband intercombination line. And I think if I'm doing well, I can cover the first theme within the coming, 1 hour and maybe a bit more, and leave the second theme for tomorrow, for Friday. Okay. So this does not work. My group is located in Hamburg, in Germany, northern Germany. This is a picture of the center of the city. And you see there's a lot of water there. And this is a picture of my group, something like 1.5 years ago. And these are the people that have been involved in the work that I will cover partly today. There's theory support by Ludwig Mattei's group, together with his postdoc Jason Cosma, which is very important for our experimental work. And obviously, working with cavities, we have an experimental team, which is consisting of Hans Kessler and Christoph Georges, who are, Christoph is a PhD student and Hans is a postdoc. And then there's the calcium team, the people who've been working on the making a super-radiant laser with an intercombination line. There's a postdoc, Hannes Winter, and Torben Laske is the PhD student on this project. Well, this is the outline, summarized in a few basic sentences. There will be the quantum many-body physics part, where the topic is, or the theme is, to create infinite range interactions by using atom-light coupling in a very high finesse optical resonator. And I will go through a number of topics here. I will start with some basic remarks on atom cavity interaction and sort of point out the different kinds of regimes where you can be, and basically guide you to the regime where our experiment is working. And I will show you that important property of our cavity is the fact that it is resolving the recoil, and I will explain to you what I mean by that. There's something that I call a scattering blockade that comes with the recoil resolving property. And then I make a little detour in something, that is my contribution to metrology. Many of you are into metrology, as I understand. So I will discuss a little bit how you can use a cavity to make an in situ monitor for Bloch oscillations, which is a possible method to increase the data measuring speed in experiments where people try to measure little g using Bloch oscillations. I will then show you what I mean by cavity-assisted matter-wave superradiance, and then go to a coupling scheme where there is an interesting self-organization phase transition and also a Mott insulator of cold atoms trapped in a cavity. And well, for the moment, you may not have to understand what I mean by that, but I will go into that, obviously. And then I will talk a little bit about, well, let's say how to simulate light-induced superconductivity with our system, or aspects of light-induced superconductivity by modulating our system externally. Yeah, and later on, this will be tomorrow, I will talk about our super radiant laser with calcium atoms, and well, I will make a few words about what I mean by a super radiant laser as compared to conventional lasing, and I will show you how we provide inversion in our specific calcium system, and then I will discuss mostly I will discuss pulse delay statistics, so the possibility to well, sort of make the fact visible that the pulses that are emitted by these super radiant lasers, if you at some time create inversion, these pulses are delayed due to the arrival time of the first spontaneous photon that triggers the pulse, and we can measure the pulse arrival time statistics in our experiment. Okay, so we have atoms and photons in our cavity, and well, the main point about having the cavity with respect to the possibility to do interesting things in the direction of many-body physics is that at the same time atoms act to shape the photon state, and the photons act back to shape the atomic state. So basically, from the many-body viewpoint, you can say that the photons being exchanged between the atoms put into the cavity mediate a retarded infinite range interaction between the atoms. This is how it at the end comes out in our experiment. And retarded, the infinite range interaction is retarded in our experiment because the photon lifetime in the cavity is so long that it takes time for the photons to rearrange with respect to the atomic state, and the atomic state again takes some time to rearrange according to a specific light state in the cavity, and these range times for the two sort of parts of the system to arrange with respect to each other, these timescales are pretty much the same. There's the recoil time on one hand and cavity lifetime on the other are not all that different. So, yeah, there are characteristic parameters that you've run into if you work with cavities, and I think most of what I'm saying here is sort of pointing at things that Helmut has been talking about in more detail. Well, one important quantity is the electric field per photon. This is the electric field that you get if you put one photon of energy h bar omega into a mode with a mode volume V. And in our standing wave cavity, the mode volume is connected with the radius of the mode, W naught squared, and the length of the mode, L. So that is the amount of electric field you can have from a single photon. And then there's the Rabi frequency per photon. So if you have a single photon in your cavity interacting with an atom that has a dipole moment d, what is the Rabi frequency per photon? And this is little g, and I think Helmut also calls it little g in his considerations. And then if you know what the Rabi frequency per photon is, you can write down what is called the single atom resonant cooperativity. This is what I call C naught, and well, this is G squared divided by kappa. Kappa is the photon, the reciprocal photon lifetime, or 1 over the photon lifetime, and gamma is the decay rate of the dipole, the atomic dipole. So if you look at this quantity, you will probably immediately see that since G contains D and G squared obviously contains D squared, and D squared contains gamma. So this constant C is independent of atomic quantities and fully is only depending on cavity parameters. And this is expressed by this equation that you can say that C naught is nothing else but 4 times the Purcell factor. And the Purcell factor is, well, a combination of quantities that only concern the cavity. This is the cavity finesse. You have heard about that by the seminar of Fritz Riele. And W naught is the mode radius, and K is the wave number of the photons that we're talking about. So there's this relation, and I will tell you in a moment what the Purcell factor means. So then, if you know what the single atom resonant cooperativity is, then it's also interesting, at least for our experiment, which are operating very strongly detuned from atomic resonance, the single atom off resonant cooperativity, which is simply C naught divided by 1 over delta over gamma squared. So delta is the detuning of the light we use from the atomic resonance. And in our case, this is a very large number. So this is reducing the single resonant cooperativity by a substantial factor. Yeah, and then you can ask yourself, what is the cavity resonance shift per photon? Yeah, how much do you shift the resonance per photon? And this is the quantity I'm writing here, 1 over 4 times C delta. And if you express that in terms of C naught, you see that in terms of G actually, then you see instead of G squared divided by kappa and gamma, you get G squared divided by 4 kappa and delta. So this is a typical light shift expression. This is the shift that corresponds to a single photon. What I mean by these quantities and how they sort of come into play if you work with cavities. This is what I will try to describe in my next 3 transparencies. So if we're talking about cavities, there are a number of properties of these cavities which make them interesting and which are important for the physics. And one is the ability of a cavity to store photons. Obviously, a cavity is a trap for photons, and a most important quantity is the lifetime of the photons. How often do the photons bounce back and forward between the mirrors before they are ejected from the cavity, maybe through one of the mirrors or via scattering from roughnesses of the mirrors into free space. And this is a typical curve that you get if you do this kind of experiment. You shine a laser beam onto your cavity, you switch off the laser beam at some time, and then you watch the photons leaking out of the cavity, and you see an exponential decay. And in our experiments, we typically have something like 18 microseconds photon lifetime. The photon lifetime is directly related to kappa. This is the photon escape rate from the cavity, and kappa in turn is directly related through the width of the area resonances of the cavity. So we have fairly small value of kappa, and corresponding to that, the cavity bandwidth, the width of the cavity transmission resonance is extremely small in our cavity, on the order of a couple of kilohertz, since our finesse is 350,000. There's the ability of a cavity to modify the quantum vacuum. This is maybe a fancy way of talking about the fact that the scattering properties are modified by the presence of a cavity. And what I mean by that is the following. Imagining a cavity and you put something into the cavity that can scatter photons. Then you can ask yourself, what is the rate of a photon to be scattered into the cavity mode as compared to the rate of scattering this photon into any of the free space modes, to anywhere aside from the cavity mode. And this factor has been first described by Purcell in the 50s, and it's a factor that can be directly related to two quantities. That is the power enhancement factor of the cavity, which is directly related to the finesse, how good are the mirrors, and the angle, the mode angle. Obviously, the larger the mode angle, the easier it is, the more probable it is that the photon is scattered into that part of space. So altogether, eta is 12 times the spatial angle of the mode times the power enhancement factor. And finally, there's the ability of the cavity to detect polarizable particles. And what I mean by that is the following. If I have a cavity and I put an electric dipole of any kind into the cavity, and I can ask myself, how does that affect the cavity resonance profile, the spectral shape of the resonances? So what will happen is the presence of the electric dipole will, in principle, act as if there's an index of refraction medium inside the cavity that shifts the resonance by changing the optical path in the cavity, and so what happens is that the transmission resonance will shift a little bit, and delta naught, that's a shift of cavity resonance per particle, is given by this formula, and you see that due to the fact that we are strongly detuned, there is a large denominator, and here we have the cavity, the photon decay rate, and this is the Purcell factor, which in our case is a little larger than 40. Yeah, we will see what that means in a moment. If delta naught exceeds kappa, we talk about the regime of strong coupling. Which means that a single particle, like an atom, can shift the cavity by an amount such that we can immediately detect this. And then finally, there is two different regimes in terms of dissipation that plays a role in our experiments, and this is the difference between these two regimes. Either the recoil frequency is much smaller than the cavity decay rate, and this would mean that if you apply a photon of frequency omega p and you tune the length of this photon such that the cavity resonance allows you to make a scattering process transferring 2h bar k to your atom, going from here to here. Yeah, then the next step, going 2h bar k further on this momentum axis, is also possible because kappa is very large as compared to the unit on this y-axis, right? So it's no problem to do scattering processes first going from here to here, and then a next scattering process can happen and you increase your momentum in each of these steps. And this is to be compared with the situation when kappa is smaller than the recoil energy. You see the recoil energy is a unit on this axis here. Then the situation is depicted here. And you see that, well, this distance here on the y-axis corresponds to kappa. And if you make one scattering process, then the next scattering process is not possible anymore because the cavity does not support this process resonantly any longer. And in that sense, there's a blockade of scattering after a single photon has been scattered. The atom cannot anymore scatter a further photon. That's the situation where we operate in. So, and then finally, if one puts that all together, one has different regimes. One can talk about different regimes which are connected with these different kind of parameters. The Purcell factor, if that is larger than 1, it means that the cavity is sort of like a vacuum cleaner sucking in all the photons. Most of the photons are scattered into the cavity, and you do not scatter a too high fraction of photons into free space modes where you lose the photons. This is important if you want to do efficient cavity cooling. Yeah, there is another regime where n times the shift, the cavity resonance shift per particle exceeds kappa and gamma prime. Gamma prime is the scattering rate, the spontaneous scattering rate, or optical pumping rate, if you want. And if this is the case, then, well, the atoms, n atoms that you have in your cavity shift the cavity resonance by more than the cavity line width, or damping through spontaneous scattering. So this is then what you call the strong cooperative coupling regime. And we also have the regime of resolved recoil, where 4 times the recoil frequency exceeds kappa. And we are in the center of this picture. Obviously, the picture is plotted in a way that we can be in the center here. So this is our cavity. To summarize that, the distance between the mirrors is 5 centimeter. Well, I'm showing that because we are experimentalists, and that's the real world here. I will bug you a little bit with these kind of experimental numbers as well. Our finesse is 340,000. The line width is 4.5 kilohertz, which corresponds to the recoil frequency, which is 3.6 kilohertz. So this is pretty much the same order. The Purcell factor is 44. We have typically 100,000 atoms in this cavity. What we do is we produce a Bose-Einstein condensate of rubidium atoms and place it right in the center of the mode. We use a very large atom cavity detuning of 8 nanometers. Spontaneous photons are completely out of the game. There's no spontaneous scattering. The kind of scattering that I'm talking about is basically Rayleigh scattering, that atoms only act as an index of refraction material. So in principle, it could be something else. It could be dust particles, or as far as the contribution of the atoms goes, it's just index of refraction. The shift of the cavity resonance in presence of the Bose condensate of say 100,000 atoms is typically a factor larger than 1 times kappa. So we are operating in the strong cooperative coupling regime in these experiments. And this is kind of a cartoon of the experimental protocol. Actually, all this has to be thought of being rotated by 90 degrees. The cavity is oriented in the real world vertically, but it's more easier to show it like that. So typically this is the cavity mode with a BC placed inside this mode. And to know the instantaneous length of the cavity, we have to lock the cavity to another laser, which I call the reference laser, which is incoupled into the cavity using a 1-1 mode, a transverse mode, such that the Bose-Einstein condensate does not see much of that mode. These photons should not disturb the Bose condensate. That is possible. And then we use the reference beam to derive the beam that we want to use for interacting with the photons. And that gives us the relative stability, which is a crucial point in our experiments, because the cavity has this extremely small bandwidth of a couple of kilohertz. So we have to exactly know what is the frequency of the beam that interacts with the atoms relative to that very narrow resonance. And this is the way we can do it in a fairly simple way. Okay, what we can also do is time of flight experiments where we simply turn off the trap. The atoms are held by a magnetic trap in this mode, and we can turn this off, and then the atoms basically fall and expand, and then if we expand for a long enough time, we can take a photograph which gives us a picture of momentum space. So we can take look at momentum spectra. And to show you a more realistic sort of view of what is in the vacuum chamber, there is the coils for making the Bose-Einstein condensate, and just to give you the sort of the scales, this is a coil size 50 millimeters, and this is a 7.6 millimeter diameter coil. The cavity is arranged vertically, and yeah, so the mode is sort of going through the center of this coil, and the Bose condensate sits here in the middle. And actually, to make the Bose condensate, we cannot make it exactly already in the mode between the mirrors, but a little aside, and then we shift the Bose condensate magnetically and place it very precisely in the center of the mode. And we can do that without disturbing the lock of the cavity, which has to be well, very stable and should not be disturbed by pushing the BC right in between the lobes of the 1-1 mode, right into the center of the 0-0 mode. Okay, so that's all I will say about the experimental, the technical part of doing these experiments. There are different scenarios of how one can couple light to the cavity. Obviously, the most natural way is to couple axially, but well, we can also shine light from the side onto the atoms, and we can do that with a traveling wave or with a standing wave. And each of these schemes I will show you in action in the following. So let's start with axial coupling. So we have a beam coupling along the cavity axis to the resonator, and if we look at momentum space, these are the momentum states that are accessible for scattering. So if we place BC at time t equals 0 in the center of the mode, and we neglect interaction for a moment, we well, sort of model our atoms as independent atoms which are not interacting, then we can think of the BC being represented by atoms in the 0 h bar k state. And by scattering photons along the cavity axis, we can go to these different momentum modes. And this is shown here, like if we shine in a blue detuned photon, blue detuned with respect to the cavity resonance, we can make a transition which applies 2 h bar k momentum going from here to here, and just as well from here to here. And well, the energy that's transferred by this scattering process is 4 times the recoil energy. And as I said already, since kappa is significantly smaller than 4 times the recoil energy, after that, nothing more can happen. Like once we are here, we cannot go up and we will not be able to come back. However, if we now couple in a red detuned photon, then it's possible to bring both of these momentum states back to the 0 momentum state. Yeah, and yeah, that is something you can directly look at in experimentally. So what we're doing here now is the first step, starting with the BC and exciting by scattering a photon to bring the atoms into the plus minus 2 h bar k states. And what happens is that as you do that, there are the photons that you send in, which are blue detuned with respect to the cavity resonance frequency, and there are photons at the cavity resonance frequency emitted into the cavity. So what you see is a beat between these two frequencies. This is the signal that comes out of the resonator through one of the mirrors, right? So when you see an oscillation, which is simply corresponds to 4 recoil frequencies, 4 times the recoil frequency. And after some time, this beat dies out and the atoms will be completely transferred to these 2 states. And then you can take a momentum picture and you see that this has really happened. After that, you can add a red detuned beam. You can couple in a red detuned beam for some time and recombine the 2 fractions again at k equals 0. And again you see a beat between the photons you've sent in and the photons emitted resonantly into the cavity. This is here. This is the first step here, shown here. And then I add a second pulse of red detuned light, and again you see the beat, and after some time the atoms are sort of reunified. Okay, so this is the sort of the typical thing that you see if you do axial coupling, and you can, well, obviously use that if you want to put together a cavity cooling scheme by using many of these pulses, red detuned pulses, starting with a sample that is not yet a Bose condensate, but occupying many higher lying momentum states, and these pulses will very efficiently cool and bring the atoms back to your condensate state. In our experiment, this is unfortunately not very easy to do because we have to compress the atoms quite a bit with our magnetic trap to make them overlap with the very narrow focus of our cavity mode. And if we heat it a little bit to demonstrate this kind of cooling, then very quickly we are not interacting with the mode anymore, and that limits us. So this is not an experiment designed for cavity cooling, but in principle you can do that, yeah?
When you take the first picture for the BC, you don't kill the BC?
No, the BC is sort of still alive because all that is coherent. Yeah.
The imaging beam is on resonance or off? How you image this BC?
Oh, the BC is, this is destructive. Yeah, obviously for each of these pictures, a a BEC has to be made, the full experimental protocol has to be executed, and then you can make that picture. So after that, the BEC is destroyed after you made the picture. But to make this picture, we have left out making this picture, obviously. So we just do the experiment with both steps, and only at the end we make a picture. But we know what happens if we take a picture in between, then it looks like that. Okay. So now I want to make a little bit of a detour to show you that coupling light axially to our cavity can be used to do something useful. And something useful, metrology obviously is an example. So I just want to sort of remind you of experiments that have been done by different groups, but most prominently I think by Tino's group using Bloch oscillations to measure acceleration, little g. And he has been, during the years, been pretty successful to get to well, sort of notable precision. You see in an experiment in 2011, he has measured little g to some amount of digits using Bloch oscillations. And it's not quite as where you can go with, at that time, it was not quite as where you can go with other techniques, but already very close. So, yeah, in this experiment, there is a problem, and the problem is that if you measure your Bloch oscillation, it has been done destructively by doing time of flight expansion and making destructively taking an image with resonant photons. So each point on your Bloch oscillation basically requires to make a new BEC, and so the speed of data acquisition has some limitations due to that. And then the question has arisen already some years ago whether using a cavity you could monitor the sort of oscillating wave packet in your lattice through the photons coming out of the cavity. And there have been two publications by theorists who have looked at that in ring cavities and standing wave cavities, and they have predicted that should be possible, and that the Bloch frequency you should measure in these experiments should be equal to the Bloch frequency you would observe in absence of a cavity, which is crucial, obviously, that you don't measure something related to the cavity rather than the Bloch frequency. So, well, now just to remind some of you, I don't know, maybe I can even leave that away for most of you. Sorry if most of you know that already, but I thought very briefly I revisit Bloch oscillations and tell you in three words what it is. So if you have a wave packet and a lattice, and the wave packet extends over many lattice sites of your lattice, then well, basically the dynamics has to be described by looking at the band structure, right? And now we are talking about the lowest band, the ground state band, which typically looks like that in such a simple one-dimensional lattice. In the tight binding approximation, you can write it immediately write it down. It has this form: some constant times cosine q times d. D is the lattice constant, and q is the quasi-momentum. So this is the first Brillouin zone. This is the lowest band, and our wave packet is now fairly sort of compressed as compared to the size of the first Brillouin zone because in our configuration space it extends over many lattice sites. Otherwise we don't have coherent oscillations. So that's the regime where we are. And then you can calculate that what's happening is that as your wave packet approaches the edge of the first Brillouin zone, there is Bragg reflection that takes it back to the other side of the Brillouin zone. And so you can imagine that instead of a linear acceleration, a force will simply yield an oscillation. As long as the force is not too large, then you would excite the wave packet into higher lying bands, which you don't want. But as long as the force is not too big, you induce an oscillation with a characteristic frequency that only depends on the force and the lattice constant d. And the lattice constant is very well known for optical lattices because wavelengths are so well known. So you can directly measure your force. That's the idea. Okay, so yeah, and now I'm showing you that if you do that in a high finesse cavity, and in our case we are in this cooperatively strong coupling regime. In that case, we can directly see the Bloch oscillation in the signal that comes out of the cavity. So the light photons leaking out, they make an oscillation showing the Bloch frequency. So this is just a small section of this oscillation here, where the atoms are approaching the edge of the Brillouin zone and jumping to the other side. That's where the Bragg scattering takes place. Okay, so now why is that the case? Well, simply we have to sort of resort again to the picture of the first Brillouin zone. Let's say we start with our wave packet here at k equals 0. The wave packet then will have this kind of shape. It will have a strong constant. I mean, we are at k equals 0, means we have a large offset, and we have a little bit of lattice commensurate wiggle on top. This is the shape of the wave function at the vicinity of k equals 0. And then as we move towards the edge of the Brillouin zone, the wave function will more and more turn into something like that. So the contrast of this lattice commensurate wiggle will be getting larger and larger, and at the edge of the Brillouin zone, exactly here, it will be fully turned into a standing wave. Well, if you have a grating, a fully developed grating, then your Bragg scattering will be the light can be Bragg scattered very easily, and that basically enhances the atom-light coupling. So the closer you approach to the edge of the Brillouin zone, the stronger your coupling constant will be. And well, if the coupling constant changes, what happens is that the cavity resonance will change. Basically the optical path in the cavity will change, and this means that as your Bloch oscillation evolves, what happens is that your resonance moves back and forward. And now it depends where you put in your the light that you couple in, at what frequency is it coupled in. If it's blue detuned, then you are on this side and the resonance moves back and forward, or if it's red detuned, you're on the other side. And depending on that, you will get a different phase of your oscillation that you see in the transmitted light. And this is shown here. This is the experiment here. Here you see the Bloch oscillation, and that is the calculation. Well, you see that in our experiment we are not well set to see many Bloch oscillations because our atoms are strongly interacting via contact interaction. Collisions are a very serious effect in our cavity. This is why in real experiments where you want to work with Bloch oscillations to measure little g, you turn off the interaction by some means, either working with the right kind of atom, like strontium 88, that would be a good candidate, or you use a Feshbach resonance to tune the interaction to zero, because otherwise you get dephasing of your Bloch oscillations, which is not what you want. So for us, this is just a demonstration, kind of a proof of principle, and we cannot do really precise metrology. Question?
Since you are working in a DC regime, why don't you go to fermions? Of course, they don't form DC, it's clear, but they also don't interact with the other.
You imagine that one could work with a thinner ensemble, right? But we cannot do that. If we go to much lower atom number, then we are not in the strong coupling regime anymore, and then the picture that I'm telling you doesn't hold anymore. So we need the strong coupling. But on the other hand, we also need to have all the atoms within the mode. And the mode is very thin. It's the mode radius is only 25 microns. So we cannot afford to expand the atoms, to make the trap more shallow. We have to compress. So our density is necessarily like a few times 10 to the 14 per cubic centimeter, otherwise we cannot operate.
So you're saying that if you go to cool fermions, you cannot get that densities as high as in DC?
If you would use ultra-cold fermions, things would be better, because I mean there's still, it depends, like ultra-cold fermions will still be more expanded as compared to bosons. That's better, and they don't interact if they're single spin. So you're quite a bit better off, but even better using a boson that does not interact. Like you can still make a condensate, and yeah. Okay, so yeah. So this is once more showing typical data traces. This experiment, this is the calculations, and you also see something you might expect. These different curves are for different lattice steps, and so you see that for a deep lattice, you get a situation that's represented by the red trace here, and this is a corresponding theory, and you see that basically it is more or less a harmonic oscillation. Well, there's noise, obviously, but the theory at least tells us it's a harmonic oscillation. Whereas if you are in a very shallow lattice, then you see higher harmonics, which are predicted in theory, and I think you also see it in the experiment. And this is simply due to the fact that if you are in a shallow lattice, then your band structure or your lowest band is basically a parabola aside from a very small region around the edge of the Brillouin zone. Whereas if you're in a deeper lattice, you're in the tight binding regime, where basically your first band has kind of a cosine shape. So if you now remember that the velocity that you get is simply the derivative of the band structure with respect to the quasi-momentum, then a cosine will lead to a sine. So this is like this single frequency that you see here. Whereas if you have more or less a parabola at most of the places, then you more have like a kind of a sawtooth type oscillation, which has higher harmonics. And this is what you see here. Okay, so yeah, now I want to speed up a bit. I'll show you here that where the Bloch oscillation that you see in the transmitted light and the one that you can measure by doing momentum spectra in the conventional way, the frequencies are the same. And also, we have looked at the dependence on of the Bloch frequency on all sorts of cavity parameters. And you see, we've changed the effective cavity detuning, or the number of atoms, or the number of intercavity photons, and the Bloch frequency, as far as we can see in our experiments, does not depend on that, like the theorists have predicted. But as I also said already, we cannot be very precise in our measurements. So this is something that the people who want to use that in a real metrology experiment would have to check. How well is that really fulfilled? Okay, so then let me go to a different coupling regime where photons are impinging on the Bose condensate from the side. Now, interestingly, the kind of coupling that you use leads to quite different physical phenomena in a way. We will see what happens here. This is already, will still lead to things that kind of resemble what we've seen for axial coupling in 1D. But if we take a second beam from the right, which I will talk about in a few minutes, we'll see that things change dramatically. So now let's start with a single beam from the side. So in that case, the momentum states that are accessible by scattering processes, scattering a single photon from an atom in the BEC, this is what it looks like. And what one has to keep in mind is, again, due to the fact that our cavity, our kappa, our cavity lifetime is so long, well, we have to consider the difference in energies, kinetic energies that are to be transferred in going from here to here. So all the processes indicated by red arrows, they are connected with an energy transfer of 2 times the recoil energy, whereas all the blue arrows indicate processes that take 6 recoil energies transfer, and here's the shell of 10 irrecoil processes. And yeah, what I want to do is simply show you one example of what you can look at in our system. This is if you tune the cavity to be resonant with a 2 irrecoil process. Since kappa is small, we can tune the frequency of our photons that are coming from the sides such that only the processes indicated by red arrows are possible. So basically, starting with the Bose condensate in the 0,0 state, the only thing that can happen is that we excite to these momentum state 1,1 and 1 - 1 h bar k, and then finally end up in 2,0 in that state. And after that, nothing should happen anymore. That's kind of similar to what I've shown you in 1D. And now this process is interesting in the sense that it's super radiant in the following sense. If you are in the Bose condensate state, then in configuration space, you have basically approximately a homogeneous distribution of the density. And this means that scattering of photons is destructively, it interferes constructively, and it's suppressed by the fact that for every atom that in principle can scatter a photon 90 degree, or that's the kind of scattering process that we have. We can scatter only into the cavity. Remember, the Purcell factor is 44, so there is no scattering in other states. That's relevant. So 90-degree scattering is the thing we have to talk about. And if you have one atom that scatters a 90-degree photon, there is always one other atom, 1/2 wavelengths away, that can also scatter 90-degree. And these two processes interfere destructively. So scattering cannot occur. Like in a piece of glass, if you send a laser beam through a piece of glass, there's only forward scattering. That's the only type of scattering that's constructive in terms of interference. So what you need to get 90-degree scattering is some kind of inhomogeneity in terms of the density. That's what you need. And you get a little bit of that because these are atoms in a Bose condensator, and there are some density fluctuations. So there's quantum noise, or maybe a little bit of thermal noise if this is a thermal sample. So what happens at some point, there will be a little bit of scattering, and immediately if you scatter a few photons, then you get a little bit of a standing wave in your cavity that interferes with a strong incoupling pump beam, and that leads to a two-dimensional grating of light. So you get a light shift potential, and this light shift potential induces forces upon the atoms, and the atoms will arrange in that light shift potential and are dragged with the light shift potential in a way that there is a density grading coming to existence that moves with the momentum h bar k. So this is when we have atoms in the 1,1 and the 1-1 state. And then scattering can go on, and if you're going to the 2,0 state, again, the density distribution is homogeneous again. So the scattering that is strongly enhanced through constructive interference from this Bragg grating is then suppressed again. And now you can understand how the scattering process sort of, first is initiated by a fluctuation, a density fluctuation, that leads to a Bragg grating. All of a sudden, there's kind of an exponential process that enhances scattering through the fact that the Bragg condition is fulfilled. And as soon as you get to the final state, this Bragg grating self-terminates and disappears again, and nothing can happen anymore. So that is what is expected here, and this is what you see in the experiment. This is a time axis, but this is also an axis where we ramp up the intensity of this beam. And this is done linearly here, so the pump strength is growing as time goes, and when we do that, basically for a long time nothing happens. The blue trace is the transmitted intensity. This is the intensity, the photons leaking out of the cavity, and you see at different instances of time we have taken pictures here of the Bose condensate, and you see nothing happened. The Bose condensate is well off. Only when we get to this time here at 3, all of a sudden there's this transfer of momentum starting, and you see that there's a superradiant pulse emitted into the cavity. A spike of light is emitted into the cavity, and after that, around here, 4, 5, 6, you see that the entire population is transferred to h bar k. Everybody is here, and nothing is happening anymore. So it looks like that. This is very much in accordance with the expectation. One can also do that, and I will be very brief on that, by dialing in other frequencies, doing this with frequencies that are resonant with the 6A recoil process. However, since the atoms start out in the 0,0 momentum state, the first thing that has to happen is a 2A recoil process, because that's where the atoms are, and the 2A recoil process is not resonant, so it takes some time before that process can happen. But the process, the 2A recoil process, cannot fully finish, meaning that all atoms are transferred from here to here, because immediately as these states are occupied, the 6A recoil process, which is resonant, starts to take the atoms out of these states, and it destroys the grating that supports the 2A recoil process. So there's a kind of a subradiance effect. The 6A recoil process destroys the grating that's needed to allow the two-way recoil process. And this is why a good amount of atoms is remaining in the Bose condensate and cannot be taken out. Okay, you can ask me later on details on that. So now I want to go to another seemingly related coupling scheme where instead of one beam, I have two beams. And now we will see that this leads to interesting new physics that is quite different from what I've shown you so far for single beam scattering, where you kind of are looking at something you can call matter wave superradiance. There's an experiment of Wolfgang Ketterle's group at the end of the 90s, 1999, I think, where he has just scattered photons from a Bose condensate without a cavity. And he could also see that there's momentum states, discrete momentum states populated. So here we will run into something quite different. Actually, this is something that has been very early proposed by Helmut and co-workers in a PRL paper where they predicted a self-organization transition in such a scenario. But at that time, this was formulated not for BC, but for a thermal sample. And very soon after, there has been a very nice experiment by Vladan Vuletic's group, who basically realized that experimentally, and they have shown that there's a self-organization transition in this scenario. And I will explain to you what I mean by a self-organization transition. And then later, there has been a new sort of step in this in 2010 when Tilman Esslinger's group have repeated basically this experiment, well, kind of, but using a Bose-Einstein condensate and not a thermal sample. And they pointed out that then this self-organization transition in a certain range of parameters close to the transition boundary is pretty well described by the Dicker model. So that is in that paper. Okay, so why is there new physics arising here? Well, if we are in a situation where we shine blue detuned light, and blue detuned means blue detuned with respect to the cavity resonance. If we do that, then the only thing that we can expect is that the system is excited. So we start with a Bose-Einstein condensate here in this momentum state, and we shine in a photon that's larger or longer than the photon resonant with the cavity. So the only thing is that we can go up here and excite our system. However, if we shine in red detuned photons, in principle it's conceivable that the photons that are scattered into the cavity, they are piling up in the cavity in order to make a lattice, a light shift potential, which can trap atoms in some low-lying band. And once this is established, then this lattice can sort of self-support by fulfilling the Bragg condition for 90-degree scattering. So it is, I think, hopefully clear that there is an expectation that for red detuning you might have something new than simply exciting the system. And this is in fact the case. And well, I want to approach to give you an understanding of how this process that leads to a self-organized optical lattice arises. And I'm trying to do that with these pictures here. This is a situation when I simply have a standing wave, no photons in the resonator, and this is the light shift potential, and the atoms are well, they feel a dipole force trapping them in the intensity maxima of this pump lattice. I call this the pump lattice. So the position of the atoms along the cavity axis is completely random. If you want, it's homogeneous, whereas along the pump axis, it's structured. Every lambda over 2, there's an antinode of this pump lattice that contains lots of atoms. Okay, so for this situation, this is the expected momentum spectrum. You have most of the atoms in the zero momentum peak and some atoms in the plus minus 2 h bar k peaks, which simply reflects the fact that you have a lambda over 2 grating in configuration space. Yeah? So now I already told you for the case of a single beam that in principle, for this situation, 90-degree scattering is forbidden because there's destructive interference. This also applies if you shine in a standing wave, because every atom has a neighbor lambda over 2 along the cavity axis away that destructively interferes in terms of scattering. However, there will be fluctuations of the density again, and if you crank up the power in the standing wave enough, it turns out that there's a threshold above which all of a sudden you scatter photons into the cavity. These photons create a standing wave. This standing wave is superimposed with a pump standing wave. So a 2D standing wave, a two-dimensional grating comes to existence. And in this case, since this is a standing wave, the 2D standing wave that comes to existence is a true standing wave. It's not traveling like in the single beam situation. So there's a stationary lattice that can be built up. And immediately, if there's a little bit of a lattice through very few photons scattering the cavity, then the atoms group in a Bragg grating that supports 90-degree scattering, since the Bragg condition is fulfilled. And so in a very fast process, this lattice deepens such that a strong optical lattice with localized atoms arises, and you see that by the fact that the momentum spectrum then should acquire these Bragg peaks here that show you that now you also have a lattice along this direction. And what is also interesting here is what is interesting to note is that actually, depending on the first fluctuation that initiates this process, the grating, the light grating and the density grating that can come to existence can be located at 2 different possible positions. This is like in a checkerboard where you have white fields and black fields, and there's a Z2 symmetry that's spontaneously broken in the build-up process of this lattice. So there are in principle 2 ways how the lattice can build up, and the fluctuation that initiates is that it decides which realization is realized. Okay, so there was a question, I think.
Did I misunderstand? Did you say that the pumping standing wave is traveling?
No, the pump. No, I said that if the pump wave is a traveling wave, then the lattice that comes to existence is a traveling lattice. This was this situation here. Yeah, I was telling you that here the lattice that is produced travels with h bar k momentum. And that's a crucial difference to this situation where you get a truly standing lattice. Okay, so that's what people have called a self-organization transition. Turns out this is a phase transition if you do that with a Bose condensate, and it's a phase transition that is close to the transition boundary described by the Dicke model. So this is what the theory a simple linearization of the equations of motions tells us about what is to be expected. And these are the two experimental axes that are important for us experimentalists. This is the pump detuning. So here's 0. This is blue detuning. This is red detuning. And this is the pump strength, the strength of that pump wave. And now you see that for red detuning, in fact, there's a large range where basically nothing is happening. If I crank up the pump power, I'm staying in this white region, which means that the state where you just have a BC and no scattering is possible seems to be stable. This is what the white region means. And then there's this boundary here, and if you crank up the power even more and you go into this region above the dashed line, then you see there's a color scale, and that color scale describes the deviation rate from that stable state here, which is an exponential deviation described by a rate. And this rate is plotted here, and you see white is 0 and red is large. So you're running into a situation where the both Einstein condensate state or superfluid state becomes strongly unstable. This is what the color code means. And well, this picture, this is I don't even need to describe that this tells you basically that there is an excitation mode that softens as you. These are the excitation modes that you can calculate. This is the pump strength. So we are going here for this detuning. We're going starting from here and going into this area here, like going up. And then you see that the first excitation mode softens, and this is when you hit the phase boundary. This mode is completely has completely come down to 0 excitation energy, and this is where the transition happens. So now I just want to sort of remind you that there's also blue detuning, and for blue detuning the physics is completely different. For blue detuning there is no stable phase. You see that we are also going towards a more and more white region here, but there's nowhere this excitation rate kappa really is 0. So the situation is unstable everywhere. And what happens here is that you simply excite the system, whereas here we will see that you build up a stationary optical lattice in your cavity. And that is seen in an experiment. This is the same axis, but the color code means something else. The color code means the intensity of photons leaking out of the cavity. And now you see this is the dashed line from the series plot, and you see obviously also in the experiment there is a stable region where no light is scattered into the cavity. And now as you crank up the pump strength, you are going into this colored region, actually slightly above this dashed line. The dashed line is the, as I said, the linearization analysis. It's a little above, but at some point there's a characteristic boundary, and all of a sudden photons are scattered into the cavity. And like if you go to this position here in our plot, then you can look at the momentum spectrum, and you see that indeed there is a lattice, 2D lattice has been created. You see these Bragg peaks here. These Bragg peaks are just from the pump lattice. They are always there as long as you have a pump lattice. And now you can look at what happens on the other side at blue detuning, and you see the situation is completely different. There is no place here where you can create a stationary lattice, but rather there's matter wave superradiance, just as in the case when we have a single beam coupled to the cavity, where we excite the system and superradiant pulses are emitted into the cavity, and this is seen by these spots here. This is kind of the boundary where in our experiment, the super-radiant pulses are emitted into the cavity. You see spikes of light appearing in the cavity. And this is the kind of excitation, this is the kind of momentum spectrum that you see. You see that the Bose condensate is fully depleted and the system is strongly excited into higher momentum modes. This is very different from the stationary situation that you can have on the red detuning side. And then there's also an interesting further boundary in this experimental picture here. If you move into the self-organized phase deep enough, you cross a second boundary where these momentum pictures like that turn into something completely structureless. This is like in conventional optical lattice. When you go to a deep lattice, a Mott insulator comes into existence. So this coherence of the system vanishes and the particle number becomes sharp due to interactions. So you've seen here that the dashed line does not correspond to the boundary where photons are seen in the cavity. And this is easily explained. Basically, how the plot is made is that the pump strength is cranked up linearly in time. Here, this is shown here. We are going from in 10 milliseconds, we are going from here to here. And that again means that we are not crossing the boundary between these two phases very slowly, but with a certain speed. We cannot go much slower because there are other processes in our experiment that sort of limit the lifetime of our atoms. So we don't have all the time we would like to. And we cannot go slow enough to really find this transition line, but rather what we are doing is a quench into the self-organized phase, such that the system does not have the time it needs to immediately adjust once it feels this phase boundary, but it takes some time before it realizes that now it has to happen. And this is seen here. This is a plot where we tune across the phase boundary. This is the equilibrium phase boundary, if we would be able to go infinitely slow. And what happens is on the blue curve, we are going into the self-organized phase. We stay in the superfluid regime, even though we are already above the threshold. And then all of a sudden the system realizes, now I should go back to where I belong, and going up to this curve. And then on the way back, we tune out of the self-organized phase again, and you see how the system behaves then. This is the red curve is going out and the blue curve is going in. And then you can look at these different instances of time. How does the momentum spectrum look like? And you see that even though we are across the phase boundary for the equilibrium situation, like at A, we are still fully in the Bose condensate with these black peaks due to the fact that we have a pump lattice. And only if we are here at this situation at B, you see now we have a lattice. And at C, we also have a lattice. And on the way back, when we go out at point E, we are back to the Bose condensate with a little bit of boogie of excitations on top. So this just shows that this is not completely adiabatic, but a quench. So at the end, we have a few excitations on our Bose condensate. Okay, my time is really running, and so I skip that. And I have 7 minutes. This is not long. So I want to show you what happens when you use modulation techniques that have been used a lot to introduce interesting physics into conventional optical lattice. I don't know how much most of you follow these quantum gas experiments. They are optical lattices, conventional optical lattices, standing waves. You fill atoms in very low temperatures, and then the question is that how interesting can that situation be to simulate, to model things that in electronic condensed matter happen, like can you make a quantum Hall phase in an optical lattice? These kind of questions people are dealing with. And the band structure typically, at least for bosons, the states that you can have in the lowest band are not limited in terms of structure. So what people do is instead of just working with the stationary lattice, they shake the lattice in different ways. They can shake it like on circular trajectories and all sorts of other interesting ways to do that. And what happens then is that they can describe the situation by effective models where you have something more interesting. Your lattice geometry is altered in an interesting way. People then say that they basically they emulate artificial gauge fields in their lattices, and this just means that the tunneling amplitudes are equipped with non-zero phases, and then you can have phase patterns that are can be quite complex, and that leads to all sorts of interesting new physics. And one thing that has been done with conventional optical lattice by these people here is to show that by modulating this lattice you can tune a superfluid lattice into a Mott insulator, for instance, just by shaking in the right way. Yeah, that's something that many people use. And one aspect of these kind of shaking protocols is that typically it's very hard or it's not possible to enhance coherence. Usually you always go to a less coherent state if you do that. But there has been one example in condensed matter actually where people also used shaking techniques applied to cuprate systems where they could show that superconductivity can be sort of supported or can be restored by doing these, by applying these shaking techniques. And this is a group at Hamburg by Andrea Cavalieri is doing these experiments where they have shown that by shining in very intense light pulses on cuprate compounds, they can make these compounds superconducting above TC. And they, for a very short time, they can even get close to room temperature. It's only for picoseconds, so it's not usable for anything useful so far. Okay, so I think, let me see, it's just a few, I don't think I'm gonna make it in 4 minutes. So I will rather take this to my next, to what I talk about tomorrow, right? So I start with that tomorrow. This is just another 4 pages, and then I still have enough time for the super radiant calcium laser. So then I will finish my lecture today by summing up, apart from the last point that I did not cover. So I've tried to show you, well, first discussing basics of atom cavity interaction, and then show you what makes our cavity different from others, which is the recoil resolving property. I've shown you optical mechanical Bloch oscillations as a means to, well, as I've shown you that we can make a in situ monitor for these Bloch oscillations, which may be interesting for metrology. I've shown you single beam coupling from the side, which leads to matter wave superradiance, and I've shown you what happens with 2 beams with a standing wave coupling, where you get a self-organization phase transition, and a stationary lattice where you can also have a Mott insulator. And then tomorrow I want to show you still how one can sort of simulate aspects of light-induced superconductivity with this cavity system, which is kind of surprising that that should be possible. Okay, thanks so far, and please, 2 minutes for questions.